have a guest from New York University, Daniela Huppenkothen. Okay. She has a difficult name as well.
A bit like you, and that's
well, there are more difficult names to pronounce. And, it's very nice to have her because she represents a new science branch, I would say, the data science. And she is a data scientist at NYU. She graduated last year from University of Amsterdam, where she worked with Anna. And started her postdoc at NYU in November last year as a data scientist. And she does her own work. Whatever she wants to do, she does. So today she will present her work on short bursts caused by star quakes. Magnetar.
Yeah. Thank you very much for the invitation, for the opportunity to speak here. I will present mostly stuff that I've been doing as part of my PhD in Amsterdam, but the last part is sort of part of this larger data science initiative. This is all work that I've done with many collaborators, both in Amsterdam and in New York and elsewhere. And I'm gonna try to sort of convince you that using variability in Magnetar bursts is interesting and that we can use this to constrain physics. I'm going to sort of try to unpack this title a bit, starting with magnetars and then short bursts, and then I'll talk a bit about star quakes and what we can learn about magnetars. Just for context, magnetars are a type of neutron star. I hope all of you have seen this diagram before. It's a pp dot diagram plotting the period versus period derivative of neutron stars, and the vast majority of neutron stars is here. These are the radio pulsars. And then you've got this cluster of sources up here, which if you infer the dipole magnetic field, you get dipole magnetic fields of about 10 to the 14 Gauss or so. So this is sort of much stronger. But not all of these sources, I have to say, have actually a magnetic field that's this strong, that's above what we call the quantum critical limit, where you get quantum field effects. A few are below. And actually, if you talk about magnetars, you usually talk about them from a more phenomenological point of view, because they're a class of sources that have some properties that are sort of common among many of them, but not all show all of them. So they're quite a diverse group in terms of many of the properties, but they have many of them in common. So phenomenologically, magnetars are usually either a soft gamma repeater, which we see burst in X-rays, and have seen for a long time, or you see them as anomalous X-ray pulsars, which are basically pulsars that are bright in X-rays where you don't expect them to be bright in X-rays. And all of these sources have a slow spin period that's pretty contained between 2 and 12 seconds. They're all young. Some of them have supernova association. They're all isolated neutron stars, which make it so interesting that they burst in X-rays, because there's no accretion going on. Most of them are highly magnetized in dipole components, and those that aren't, we believe, are highly magnetized in the toroidal components. They're bright in X-rays, and they're very variable. They show a rich phenomenology of bursts and outburst behavior, which I'm going to talk about in a second. And so because not all of these show all the types of behavior, the better definition of a magnetar is a neutron star source where the spin down alone cannot explain the X-ray luminosity. So the emission that you see is brighter than the energy you get from spin down, unlike for pulsars, for radio pulsars. And so the natural question becomes, where does this energy come from? And the natural answer to this is, well, you've got a really strong magnetic field. That strong magnetic field stores a lot of energy. So if you can tap into that energy, then you can explain a lot of the emission behavior that we see. And so the idea of a magnetar is that, unlike for a pulsar, even a high magnetic field pulsar, where you've got a fairly ordered magnetic field and then the standard pulsar mechanism, for a soft gamma repeater or anomalous X-ray pulsar, the fields are actually quite tangled up. And as they slowly evolve and untwist, that energy that you release during this evolution drives the behavior that we see. And in terms of the interesting questions that we can ask about the sources, the first obvious question is just, why do we see magnetar behavior at all? And why do we see it from some neutron stars? What is exactly the reason that some of these sources show bursts and show X-ray pulses and others don't? Then, of course, the holy grail question for any neutron star physics is, what can we actually learn about the neutron star equation of state, and what can we learn about dense matter by looking at these sources? And then the sort of third question, given that we have these extremely strong magnetic fields, what can we learn about the physics that occur in these extremely strong magnetic fields? And I'm going to talk, I think, mostly a bit about those two. And I have to say, I can't promise you any final answers. So, bear with me. Before I go into this, I want to show you I want to show a bit the phenomenology and put it a bit into context. And for that, I made a plot that plots the time scale of the variable behavior that you see, since I'm mostly interested in variability, and the sort of overall luminosity of this variability. And the most interesting, well, maybe not most interesting, but the most impressive variability behavior that you see is what we call giant flares. And these giant flares, this is one example from 2004. These giant flares are of the order of a few hundred seconds, but they release up to the 10 to the 47 ergs of energy. That's for a galactic source that doesn't actually get destroyed in the process. That's a lot of energy. Incidentally, this particular burst was the brightest gamma ray event that we ever saw on Earth, because it was galactic. This initial peak here saturated every telescope in the sky, and it even caused a depression of Earth's magnetic field. You could measure the effects that it had on our magnetic field. So these are quite extreme catastrophic events with a lot of substructure. But they're also extremely rare. We've only ever seen 3 since 1979. And of course, everyone is waiting excitedly for the next one, but you can't predict when they happen. They're completely random and out of the blue, and you can just hope that you have a telescope somewhere in the sky. It turns out it doesn't have to be point in the right direction because they're so strong. They go through the back of the spacecraft into the detector, and you can still see them. But then you also see intermediate flares. We call intermediate flares. They're usually a bit shorter, although this particular one isn't. They kind of look a bit like giant flares, but they're much less energetic. They're sort of the order of 3 to 4 orders of magnitude less energetic. And we've seen, about 10 of them. And then we have what we call short bursts. These bursts are really much, much shorter. They're generally of the order of less than a second. They have really rich behavior as well, but unlike these, where in the tail you mostly see the spin period of the neutron star, these are much shorter than the spin period of the neutron star. So this is all other stuff that you see, and I'm going to talk later about what that other stuff actually might be. And these are, again, much smaller in energy, but of these, at least we have thousands. They happen randomly too, but we've seen many, many more of them, which is kind of useful if you want to study them. Mm-hmm.
So this is the energy per second, so erg per second, or
yeah.
is it integrated? That's a lot. Because that's like a quasar, right? In superluminous quasar, when you have 10 to 45 ergs per second at the top. No, this should be integrated, yeah. Okay. Sorry. Yeah, okay. Sorry. I think for this one, it's kind of true, because you have this initial spike here. But yes, these should be integrated. I'm sorry. And because they're much shorter, the total energies. And then you have outbursts. I'm not really going to talk about outbursts, which are basically increase in persistent emission by a factor of about 100, and they last for hours to months. But I'm more interested in this sort of short-term behavior, so I'm going to talk about that.
There's also, some of them are transient. They're what we call burst storms, where you see hundreds of these within a day. They're glitches. Maybe some of this bursting behavior is actually related to glitches, but that's hard to tell. So there's a really rich set of phenomena, of variability phenomena, that you all need to relate back to what the physics are in some way. And I'm going to start this by talking about the giant flares, which are what most physical models for Magnetar are actually based on. And so you can see there's this initial spike that I was talking about, and then that's followed by a sort of long exponential decay with this bump in the middle and all of these wiggles. And all of these wiggles, if you just zoom in, it turns out that this is of the order of the spin period of the star, and you can see a rich sort of pulse profile that changes during the evolution. And the basic model of how you make a giant flare, this is now one model, there's several others. The basic model of how you make a giant flare is by saying, as you have these internal twisting magnetic field lines, they will slowly untwist in the core. And as they untwist, because the field lines are frozen into the solid crust because the crust is ionized, these field lines will drag on your crust. And the neutron star crust can withstand that for a while, but if you exceed the breaking strain of the crust, you might actually cause a crust fracture and a sort of catastrophic movement. And that movement releases a lot of energy into the magnetosphere via Alfvén waves. And these Alfvén waves will sort of bounce around the magnetosphere. And because you have these strong magnetic fields, you can create pair plasmas. And these pair plasmas may be trapped by closed field lines and then slowly radiate away. And this is what people believe you see in the evolution of the pulse period, is sort of slow evaporation of these fireballs. And one of the interesting points is that people expected to see oscillations, because as you fracture the crust, you expect these crust fractures to excite star quakes. So much like when you have a slip fault on the Earth, and you have an earthquake, you have a catastrophic movement, and it causes an earthquake, sometimes with quite devastating consequences. You expect similar things could happen on a neutron star. And it turns out, if you take chunks of these bits and you Fourier transform them, you form what we call this power spectrum. You can see that. You can see these spikes in the power spectrum. So this is now frequency versus power, where power measures basically emission at a certain time scale. You can see there's a spike here at 90 hertz. There's one here at 625 hertz. There's sort of lower ones at 18 hertz and at 30 hertz. And these oscillations were sort of, the fact that they exist were directly predicted by the idea of starquake models. So people thought, well, this is great, maybe there are starquakes. And went out and thought about models for how you could do this. And the simplest model that you can think of is that you excite shear waves in the neutron star crust. And these shear waves sort of excite global twisting motions of your star. The advantage of these motions is that they're easy to excite. And if you do a sort of simple-ish calculation of what you would expect to come out, it turns out that the frequencies that you expect to come out of this kind of process match fairly closely the frequencies that you see. So people thought that was great. We can use this to then think more about what this tells us about neutron star physics, because these models that you make to study the individual frequencies, they strongly depend on the composition of the crust and the general properties of the crust. So they're a probe of the crust properties, which is really useful to have. Here's just, I wanted to give you an overview. This is sort of the model I was talking about, that you have internal magnetic fields that unwind, that causes a crust failure and seismic waves. This causes Alfvén waves and a fireball, which you then see in emission. But this is just sort of one of the main models that people consider the original model. There's an alternative model where the field slowly unwinds internally, but doesn't actually cause a crust failure. The crust sort of responds slowly and plastically, but this actually causes a twist in the magnetosphere. And then you can have a catastrophic untwisting in the magnetosphere, followed by reconnection, and that actually releases all of the energy. But this can still cause, turns out, large-scale shear waves in the crust. So in either case, you could have these oscillations that we see. And so this is an example of how this relates back to fundamental physics. If you look at the frequencies, if you look at the QPOs that you see, the oscillations that you see, you cannot just say, well, I need to fit this frequency, I need to fit this frequency, I need to fit this frequency, but you need to fit them all in the same model because they need to be all either harmonics or overtones. So you have with sort of 5 or 6 QPOs, you already have some constraints of what your models can be. And it turns out, especially the fundamental, which is the lowest frequency that you see sort of at 18 hertz-ish, and what we think is the first radial overtone, which is the high frequency QPO at 625 hertz, these depend quite strongly on crust composition. So for different crust models, you get different frequencies, and particularly you get different combinations of frequencies. And this you can then make into a constraint for the mass-radius relationship, and therefore for the neutron star equation of state. Although I don't think you can do this at the moment with the signals you have. So this is a simulation that people did for an instrument that's currently proposed to fly. And if it flies, hopefully measure giant flares, although we don't know if one happens. The problem with this entire field is that with this entire picture that I've drawn, is that so far in these oscillation models, we've only considered the crust. But the neutron star crust does not exist in isolation, and this is where things become really complicated, because actually you need to think about the core as well, and in particular how they interact and how they couple together. And so in order to do this, your realistic model needs to include the magnetic fields in the core that we don't really understand. It needs to work in GR. It needs to have realistic core and crust equations of state. You need to think about superfluids and superconductors. You need to think about the structure in the deep crust. And then the large thing that we haven't talked about at all is how that actually gets translated into emission. Because the models that people build are all for how the neutron star responds and how the neutron star twists and how it at which frequencies it does this. But what we actually see is light. It's just emission that comes from somewhere on the neutron star, and how these motions on the star actually rate into emission mechanisms isn't quite clear yet either. So there's lots of work to be done, and there's lots of work that is being done. There's models being continuously developed. There are sort of 2 problems that we currently face. One of them is all the models that we have, because we have so little knowledge of many of the individual components, the models are highly degenerate. You can put in lots of different individual, you can tweak lots of little parameters and try to match them up to the frequencies you have. And this is partly because we have so little data. We only have 3 of these giant flares. So there's very little data to play with. The other problem is that in all current models, the high-frequency QPO, this sort of 625 hertz QPO, quasi-periodic oscillation that we see, is really difficult to explain. In all models that we know about, it should drain away into the core in less than a second, because the frequency of this QPO is exactly at a sort of core resonance frequency. But in practice, during the first analysis that people did, So this is the giant flare again, and here on top is the lifetime of the oscillations that we see. And as you can see, the 625 Hertz QPO, people believe, lasted for several hundred seconds. And so the question is, how could we put this together? How can our models make any sense of this? And what we decided to do was go back to the data, because when people first found these QPOs, it was in a very broad blind search without having any sort of hypothesis of where the frequencies could be, how long they could live. And so the question that we asked is, that signal at 625 Hertz, is that consistent with only with a signal that lives that long, or would this also be consistent with a short signal that could either drain away and explain what we see, or maybe be re-excited? And it turns out, if you look at this in detail, what we did here is what people call a dynamic power spectrum. So each of these points is the power at 625 Hertz for a small segment. And this width is sort of 0.5 seconds. And what we did was model the signal in detail, and it turns out that you can explain the 625 Hertz QPO with a signal that's less than a second long, but possibly re-excited several times. And that doesn't solve the problem, it kind of just shifts it, because you've now said, well, it probably doesn't live that long, which is nice for our models, but we still need to explain how it gets re-excited several times. However, that's been a problem anyway, because as you can see, some of these signals start really late in the flare, and we don't really know why they start that late in the flare. So we have a problem anyway to explain how we can get QPO started that late in the flare, much long after the crust fracture event. So that's at least, one problem that kind of goes away for the moment, or it gets mixed in with another problem we need to solve. And then I'm going to come back to this part, to the fact that we need more data, because we don't have more giant flares, and we can't really do anything until one goes off. But what we can do is look at the short bursts. Because of the short bursts, we have thousands. The caveat is that they're much less energetic, so any sort of excited signal should be less strong as well. They're much shorter, which is more a technical problem than a physical problem. And the question is kind of, are they made by the same mechanism as the giant flares or not? If they are, we expect to see possibly these quasi-periodic oscillation. If not, maybe we see something entirely different. Who knows? So in terms of the technical part, as I said, they're short duration, and the fact that they're so variable turns out is quite a problem, because the giant flares kind of look like this. You were looking for this giant needle in your haystack, because you could see in the plot they just had these giant spikes, and you're like, okay, there's something there. Our small bursts kind of look more like this. So it turns out, if you then think about this, it turns out that the standard tools that we've been using for a long time to do this kind of analysis doesn't work. And so we made some new ones. This is basically my entire PhD summed up in a half sentence. And if you're interested in the details of those methods, feel free to come and talk to me today while I'm here. And so this is what we did. We took observations. Well, the observations were already there. From a magnetar called SGR 1550-5418. This magnetar, we had the good fortune to see it go off in January 2009, where it showed over 500 bursts in a matter of a few days. Fermi GBM, the gamma ray burst monitor on board the Fermi spacecraft, caught about 283 of them. And this was really lucky, because Fermi GBM is the perfect instrument to do this. It records exactly in the right energy range, and it has an extremely good time resolution to do these sort of studies. So we were really happy to have this big data set to work with. And here you can just see an example. This is just 600 seconds of observation, and you can see every one of these peaks is an individual burst. They're just squashed together. And so all of these bursts make a much nicer, much richer data set than you have in the giant flares. So we searched these for QPOs, just the single bursts, and it turns out you find one that's left over when you try to make it go away really hard. But what we also thought, well, what happens if you have many of these bursts close by? Could it be that you excite a QPO and it drains away fairly quickly, but then you keep re-exciting it in every single burst, so it starts kind of ringing like a bell. And the question was, could you find it in when you stack bursts up? And this is exactly what we did. And it turns out you do. And now I know this doesn't look like very much, the signal's here and here. However, it's quite significant. I'm pretty confident in this, and I tried half a year to make these go away, and they wouldn't go away no matter what I tried. So we try to be really rigorous about this, because every time you report in new frequencies, the theorists go, yay, let's go and model. And you want to avoid setting them down a wrong path. The nice thing about this is that this frequency is at 90 Hertz, which is exactly the frequency that we've seen in the giant flare. And this frequency here is at 120 Hertz, which also fits quite well, which you haven't seen in giant flare, but which fits quite well into the kind of mode framework that we've been thinking about. So that's nice, because they look like giant flare QPOs. They're also kind of narrow like giant flare QPOs, and at least in these stacked bursts, they have similar amplitudes as you see in the giant flares. So that's kind of suggestive. We've since seen another one in SGR 1806-20, which is nice because that's the one that has the giant flare. So that was pretty good too. And then the other thing that we've seen was actually this weird signal here, which also doesn't look like much, but is actually quite significant in a single burst. And I'm still on the fence of whether this is actually real. But if it is, then this is something that we've never seen before, and that I couldn't explain in any other way. So these are the kind of QPO detections that we've made. But as I sort of stared at these bursts over and over again, I thought, can we do more with this? And the immediate question that we had is, what's all this other variability that was basically always my annoying noise before? But that's actually lots of variability that we can, use and think about. And the first thing that we did, because it comes naturally out of the algorithm that I used to find QPOs, is just look at this sort of power law-ish component that you see at low frequencies, which is basically a translation into the Fourier domain of these overall shapes. And if you do this, you get quite a weak correlation between the burst duration and this power law index. And what this means is that longer bursts have more variability at high frequencies, maybe, if you want to believe this correlation. And I thought, well, this doesn't tell you really all that much. In particular, having just this power law doesn't really encapsulate the richness of the variability behavior that you see. And I decided we needed something better for this. So the question that I was asking was, what's all this stuff? What's all this peaky stuff? And how can we model this? And I was mainly curious, or I was partly curious, because I'd stared at this for 2 years and couldn't quite figure it out, and it was really annoying for the QPO searches, so I wanted to get a better handle of it. But I was also interested in whether this variability relates back into the behavior that you see, the sort of random behavior that you see for Magnetar bursts overall. In particular, Magnetar bursts have often been proposed to follow a self-organized critical system, where you basically have a system that continuously drives itself towards a critical state. And when it reaches that critic without needing any sort of outward driver, and as you hit that critical state, you get a catastrophic release in energy, in this case a burst, and then you go back to a pre-critical state where you start building up again. This is usually sort of exemplified by the sandpile model. If you just have a sandpile and you randomly drop on little grains of sand, you fill in your sand pile until you reach the sort of maximum slope where you can't support your sand grains anymore. And then if you drop on a sand grain, then you get this sort of avalanche down here where it goes back to a pre-critical state and it all starts again. This has been proposed for X-ray and optical flares from the sun quite a lot, and has been very successful at explaining many of the properties you see in solar flares. And it's also been proposed for earthquakes, and in relation to that, to magnetar bursts, because it turns out magnetar bursts, if you just plot the overall energy released in a short burst and make the differential distribution of this, it follows exactly the kind of power law you expect from earthquakes and that you also expect from self-organized criticality, which is nice. So my question basically was, does the variability you see in side bursts have any relation to this kind of idea? And the other question was, can we take this variability inside that we see in bursts and relate it to maybe simple physical models? Because part of the problem is that we don't have any emission models for how magnetar bursts emit. And nobody's really ever looked at the variability before. So there's this kind of gap between the observations that we have and the theory that I was trying to fill. And for this, the first conclusion was we definitely need much better empirical models. So I went forth and talked this through with some collaborators and took a sample of bursts. These are just 6 examples to show you just how diverse it is. They're all kind of spiky, but they're all kind of spiky in different ways. And so our simple hypothesis was, what if these spikes are actually cascades of something? They could be cascades of reconnection events. They could be cascades of individual crust fractures that where sort of one triggers the other on the neutron star surface. But let's just assume they're cascades of some form. And so we can model them then as superpositions of individual little spiky events. So this is what we did. And just because we wanted to stay simple, we picked an exponential rise and exponential decay profile. But for example, if someone came up and said, for a reconnection event, the light curve should look like this function that I'm giving you, this would be really easy to put in, and actually we could do proper model comparison with this because of the way the model is set up. One special feature of this model is that we really wanted to infer the number of spikes in each burst together with all the burst spike parameters. And this is actually a fairly simple model to write down in theory. To actually then do the inference and sample from this is really difficult. But we didn't want to bias ourselves by saying we just look at it and say, okay, maybe there are 5 spikes and I'm putting in 5 spikes. We wanted to be as sort of unbiased as possible in that respect. And it turns out you can do this with a special sampling technique called diffusive nested sampling, which is really powerful on this kind of problems because it solves, or it's very robust to certain problems that you normally have with Markov chain Monte Carlo. So this was really fortunate that we could use this method and use this code, and that solved our sampling problems. And then what you get, I hope you can see this. So in black, you can see the light curve of one of these bursts. And then in color on top of there are sort of 10 random draws from the model that we made. And you can see they sort of fit the spikes really well. They usually don't get stuck too much in the noise, which is nice. And on the right here, you can see the posterior distribution of your number of spikes per burst, which lies somewhere between 10 and 20, but mostly sort of 11 and 16-ish. Which is quite nice. I was a bit scared that it would just be all over the place and just fit lots of noise, but it didn't. So we now have basically a really high-dimensional posterior distribution that we can sample from and that we can do inference with. And so the first thing I did was go back to our self-organized criticality assumption and say, for self-organized criticality, many of the individual parts, many of the individual quantities, such as the duration and the amplitude and the fluence, which is a proxy for the total energy, should form power laws that flatten off. And as you can see, at least for the spikes, none of these form power laws that flatten off in any way. And this is true both for these, and this is also true for what I'm going to show you in a minute, the waiting time distribution between adjacent spikes. So my sort of initial conclusion would be that actually while bursts overall might be a self-organized critical system, this is not true for the variability within bursts. And then the other interesting quantity that we were thinking about was the waiting time distribution, which is the distribution between adjacent spikes. And this also actually includes the distribution between adjacent bursts. So about the top peak here is the distribution between adjacent bursts, and this one is the distribution between adjacent spikes. And what this kind of tells you, if this had been just one distribution, this would have told us that the individual spikes are actually independent of each other. They just happen to be clustered together by chance. But this is not true. The individual spikes are actually causally related in some way, which is an interesting conclusion. And then we thought, in this sort of cascade model, can we make a first initial simple estimate of the kind of waiting times you would expect? And we came up with sort of 3 really simple toy models. And the first one is basically you have a crust fracture somewhere, and that crust fracture releases energy in the form of Alfvén waves through the core. And that energy sort of travels through the core. And maybe somewhere else on the crust you have another weak point where you could have some failure. And so as this energy reaches this point, you get a failure point and you get another spike. And so we made the distribution, we thought about what would the waiting time distribution look like if you just took this simple model and then put in some reasonable values. And it turns out it looks like this, where this sharp cutoff is basically the travel time through twice the radius of the star. And this doesn't assume anything like you could have reflection or anything. This is just a simple assumption. But, this clearly doesn't go together with this. Also, these are quite a lot shorter than you would expect for the distribution that we see. Sorry, that was too hard. The second model is what happens if you have a crust fracture and that energy actually travels as shear waves through the crust. And again, you reach weak points. And as you reach weak points, you get another crust fracture. And again, you get a spike. One of the problems with this model is, or with all of these models, is that you never take into account line of sight effects. So for example, you could have a crust fracture, and then it travels this way, and it travels this way, and on both you trigger your spike, but because of line of sight effects, you see them actually as 3 very short spikes after the other. So that's possibly a possible bias in this whole model. But then again, we put sort of typical parameters for shear waves in the neutral star crust, and that distribution actually looks pretty well. Looks pretty similar to what we saw in reality. It has a bit shorter waiting times that you would expect, but it's sort of within the uncertainties that we'd expect. And then the third model that we considered was the idea of just having purely magnetic reconnection events, where again you have a magnetic reconnection event in the magnetosphere. You then again release energy in form of Alfvén waves, and they trigger reconnection at another weak point, and again you get these kind of cascades. And it turns out they make the distribution that's actually closest to what we see from the real data. But of course, these are sort of really, really simple toy models, and we need much better models for this. My hope with this work was that someone would either say, that's an interesting idea, but I can do this much better, and then come back and say, here's what our much better theory says it should be, or they say, this is all stupid, it must be something entirely different, and then again I hope they would come and say, here's what I think it should be, does this match with the data? But the idea was to showcase that there is a lot of variability information, and we can tap that information and try to use it to guide theoretical developments. We're not done with this. This is sort of one of the active projects I'm working on, and we have collaborators visiting actually next week to talk this over. One of the interesting things that we want to do is add hierarchy, both across samples, because we haven't really done this properly for this magnetar yet, but we also want to compare different magnetars. And one of the nice ways of how this model is built up is that you can just add hierarchies and it all adds on naturally as part of this hierarchical model that we use. We really want to think about the energy dependence and lags that you see, because there is a lot of energy dependent behavior in there. We can use actually these models to improve our QPO searches, which is nice. So if we have new bursts or a new giant flare, we can actually use this. And then this is not really something that I'm working on, but I hope someone else will pick up, is that we need much better theoretical models of the emission processes. And this is part of the ongoing work in Amsterdam as well. And then, of course, everyone's waiting for another giant flare, so universe. The last thing that I want to sort of say is that this model is fairly universal. It's really easy to adapt to other sources, and we're currently in the process of this. I'm working with someone who does this for stellar flares, observed with Kepler, who's looking at variability there. And we have a project that we're about to start with GRBs, where we really want to improve the sort of inference that you make from GRB pulse models, and where you can actually put in physical models for how these pulses form, and then do inference in a statistically rigorous way. So this is about to be started. This was just an example that I ran this morning, where I just took some Fermi-GBM data and threw it into the model that I have, and it comes out fairly well. Okay, so my conclusions. I hope I've convinced you that magnetars are quite powerful when it comes to probing both dense matter physics and the strongest magnetic fields, and that we can learn a lot from the variability to constrain the underlying emission process, but also the more nuclear physics. And then we've seen QPOs both in short bursts and giant flares, which could indicate that there's actually a common origin of both phenomena, but the models to describe them are too degenerate to really, really say. So going back to my title, are magnetar short bursts really caused by star quakes? I think we still don't know, but I think we're on the right way to finding out. And I want to leave you with this. This is my piece of advertising. As part of the Center for Data Science, if you're interested in any sort of methods development in astronomy, as part of the more slow and data science environment, we're organizing a workshop called the Astro Hack Week in New York at the end of September, and it'll be a part summer school where we talk about, where there'll be lectures on machine learning and statistical techniques and sampling methods, and we've got a lot of really interesting experts come in to give those talks. But there's also going to be lots of free time to work on projects, and we actively encourage people to bring projects and to pitch projects and to find people to work with at the Astro Hack Week. Last year's first installment had sort of 50 participants and about 35 projects, some of which are now being made into papers, and lots of new interesting collaborations between people who would have otherwise never met. And it's pitched at everyone's from sort of graduate, advanced and undergraduate to faculty level, so everyone's welcome. Here's the website, or talk to me if you want to know more, and I'll leave you with that. Thank you.
Thank you. Lots of interesting things. Any questions? Yes.
So in these self-criticality models, you can have correlations, for example, of how, whether you have to wait a long time to get a very strong burst, so basically long waiting periods are followed by a strong burst, or whether and then it takes a long time to recover. No? So if you look at the correlation between the waiting period and the previous and following size of the next event.
For the spikes, actually no. That's something I should definitely do. For the bursts themselves, that's been done, and there's not really been any correlation. But that doesn't seem to still deter the self-organized criticality explanation, because I think in some systems, like in solar flares, I think you don't have that correlation either. Although I may be wrong about that.
But you do have it in the rapid burster,
Mm-hmm.
X-ray burster. That was
Yeah.
pointed out early on, and I forget.
But that
The following or the preceding, I think it's the preceding.
is that because you
Filling the tank with-
you build on material?
Sorry?
Is that because you build on material during accretion?
Well, it's a magnetospheric
Yeah.
instability.
Oh, okay.
It's not, these are not type 1 bursts.
Okay.
Rapid and, very different in their characteristics, but they repeat, and the waiting time is a function of
Yep.
how long of the size of the burst.
What is the typical plasma densities that you have to deal with here?
That's a good question. I would have to look it up.
Oh, transfer.
Oh, you mean in the? Do you mean in the magnetosphere or in the star?
No, not outside. In the microsphere. That's pretty nice. One thing. One other question is, what kind of likelihood did you use when you did all these calculations?
It was a Poisson likelihood.
I'm sorry.
A Poisson likelihood? Yeah. Because all our data is photon count data, so yeah. If you're interested, I can show you the details of what we used.
If I go back to the plot where you're fitting the individual time series and you're showing distributions of affluence and amplitude and waiting time.
This one?
Yeah, so you're using a Bayesian hierarchical model. So you have parameters for each individual burst or
Yeah.
time series, and then you have another layer which describes the population distribution of those
No,
parameters.
we don't have that yet. That's actually the next step that we want to do. I mean, this was sort of a first simple test to see whether there's anything in there, where basically I drew samples from all the individual bursts and then combined them to do this kind of distribution, and that imposes a strong prior on any correlations, that there aren't actually any there, which we were aware of, and actually putting on this additional layer of doing the entire population in that hierarchical model. That's the step that we're going to start
so it's not
next week.
hierarchical yet. You're just hitting individual bursts or something. On the previous
It is-
slide, you had the individual time series, right?
Yeah.
Yeah. So
Yeah.
you're fitting each one independently.
Yeah.
There's no parameters linking them together.
No, not yet.
Any more questions? Well, Daniela is just here in New York City. You can go and visit. Right?
I'm also still in Boston until the end of the week, although I'll be at MIT for part of that. So
Thank you.
thank you.
Events do you have altogether?
Pardon?
How many events?